Welcome to lecture series of network theory. Today we are doing the source transformation and the source shifting. So in the previous class we have seen in the previous lecture, so what are the different types of networks available and how we can define that and how we can classify that, and different types of sources. It can be ideal source or a practical source. Again, in the practical source there are two varieties, that is independent source and the dependent sources. So we have seen the symbol of the independent sources and dependent sources and how it can be minimized in a network. Okay, so and introduction to the source transformation was also done in the previous lecture. So today we'll do some numericals on the source transformation, and also we'll define the source shifting and as well as problems on the source shifting. So let us consider this numerical. So in this circuit they have asked you to find out what is the voltage across the 4 ohms resistor. So voltage across this 4 ohms resistor we need to find out. Okay, and also we have to find out what is the voltage of the source and equivalent resistance. Okay, so these are the 3 parameters we need to find out from this network. So before we head to the finding the what is the voltage across the 4 ohms resistor, first from the diagram we can see that the voltage source V. Okay, so whatever the current generated by this source, it is divided at this junction. Okay, it is taking 2 paths. One is I1 path, another is I2 path. This is I1 path and this one is I2 path. Okay, so the combination of this I1 and I2 current, okay, the sum of these two current is nothing but the main current generated by this source V. And also from the network we can also observe that the voltage across this 8 ohms resistor, it is given as 50 volts. Okay, so the voltage across from 8 ohms resistor, it is given as 50 volts, which is nothing but the same voltage we will observe across the 10 ohms resistor also. So what is that means? The voltage across 10 ohms resistor and 8 ohms resistor is nothing but the 50 volts. Okay, yeah, V 10 ohms, okay, V 8 ohms equal to 50 volts. Okay, and also I will be equal to I1 plus I2. Okay, so if we find out what is the total I, then we can find out what is the voltage across the 4 ohms resistor. Okay, so let us find what is the I1. I1 is nothing but current flowing through the 10 ohms resistor. So current flowing through 10 ohms resistor is nothing but voltage across that resistor, that is given from the circuit as 50 volts, and the resistor is 10 ohms. So this will be 5 amps. Okay, so that is I1. Similarly, I2 equal to 50 volts by 8 ohms. Okay, so which will be approximately equal to 6.25 amps. Okay, so total I will be equal to I1 plus I2, which is equal to 5 plus 6.25 equal to 11.25 amps. Okay, 11.25 amps. So I will be equal to 11.25 amps. So we found out what is the current which is generated by the V source. So after that we'll find out what is the voltage across the 4 ohms. Okay, so we know the current, we know the resistance. Okay, so then V 4 ohms is nothing but I into 4. Okay, so which is approximately equal to 11.25 into 4. So which is actually equal to 11.25 is 45 volts. Okay, so V4 ohms is nothing but 45 volts. Okay, we found the second parameter. Now let us find out what is the equivalent resistance. Okay, yes. So from the network, removing it. Okay, let us see here from this network. In order to find out the equivalent resistance, we have to take out the sources. Okay, it can be a current source or a voltage source. So when we take out the source from the network, we find only the resistor. Okay, connected between the terminals. So 4 ohms. Okay, which is in series with the 8 ohms and 10 ohms, which is in parallel. Again, it is connected across another terminal, that is 8 which is connected with the 3 more resistors, 8 ohms, 12 ohms and 24 ohms. Okay, so equivalent resistor equal to 4 plus 8 parallel to 10 plus 8 parallel to 12 parallel to 24. So which is equal to 4 plus 'Okay. So when you reduce all this, equivalent resistor will come around, R equivalent will be 12.44 ohms. Okay, so we found all the parameters asked by the questions. Okay, so let us move to the next one. Next question. Here in the numerical, we need to find out what is R. Okay, so in order to find, again they have given what is the current generated by the 25 volts, which is equal to 2.5 amps. Okay, and it is getting divided at this junction. Okay, so this junction, when it is divided, it is dividing into I1, I2 and I3. Okay, so once we find out what is the value of I3, okay, then we can find out the R value, provided if we know the voltage across these two terminals. Say let us name it as A and B. Okay, voltage across this terminal. Okay, so in order to find the voltage across this terminal, since 20 ohms and 20 ohms resistors, which is also connected to the same terminal as that of the R. Okay, so voltage across the 20 ohms resistor will be equal to the voltage across the R. Okay, so from that we can find out what is the value of R. Okay, so in order to find out, again we will take what is the total I, which is equal to 2.5 amps, which is also equal to I1 plus I2 plus I3. Okay, so we first will know what is I1 and I2. Okay, so in order to find out what is the voltage across this terminal, okay, so first we will find out voltage across 5 ohms is given by since I1 and I2 current flowing through the same resistor, and I1 and I2 will have the same value. Okay, so I1 will be equal to I2, okay, which is equal to the voltage across the parallel, that is voltage across A and B, that is 12.5 by 20, which is equal to 0.625. So I3 is equal to 2.5 minus 1.25 is equal to 2.5 minus 0.36. So this is the value of I3. Now we need to find out what is the value of R. So in order to find R, we know what is I3 and also we know what is VR. So VR equal to 12.5. So now to find R, so it will be 10 ohms. So R value that we have obtained is 10 ohms. So let me explain once again. In order to find the R, first we need to find out what is the current passing through this R. Okay, in order to find out the current passing through this R, the current generated by the 25 volts, okay, that is equal to 2.5 amps. Okay, this 2.5 amps at the junction A, so it is actually at this node, it is actually dividing at this node as I1, I2 and I3. Okay, so first we need to find out what is the voltage across this parallel combination. So for the voltage across this parallel combination, that is between the terminal A and terminal B, is equal to 25 minus 12.5 volts. Okay, how we got the 12.5? Because we know what is the total voltage which is across the 5 ohms and what is the current passing through that 5 ohms. So the current passing through that 5 ohms is 2.5 amps and voltage we got it as 12.5 because of the resistor. Then at this point we have a 12.5 and at this point we have a 25 volts. So the difference between this will be equal to 12.5. So once we know the voltage this node A and B, then we can find what is I1 and I2 and I3. Okay, because the I3, okay, which is connected again to the A and B. Okay, so here in order to find that, first we will find out what is the I1 and I2. Since the resistor values are equal, so I1 and I2 will be equal to 0.625 amps. Okay, so we know what is the voltage across that combination. Then we also know the total currents I1, I2 and I3 will be equal to 2.5 amps. So from these two equations we found out what is the I3. So once we find out what is the I3, okay, then we, with the help of the voltage in across the parallel combination, so that is 12.5 and just now we found out what is the I3 as 1.25, then we get the R value as 10 ohms. Okay, so I hope it is self-explanatory. Again, we'll move on to the next slide. So these numericals were very basic. Now we will move on to the next concept called source shifting. Okay, so why source shifting? Why not source transformation alone can be reduced, reducing the network? The problem is sometimes for the source transformation, the main limitation of that is that whenever in the network, if you find ideal source, okay, so when the ideal source are there, we can't reduce the network with the ideal source because source transformation works only on the practical sources. Okay, so if there is an ideal source, somehow we have to make into a practical, so we have to convert into practical source, and that conversion, okay, so that conversion technique we call it as a source shifting. And this source shifting comes in the two classification, that is again based on the which kind of source we are shifting, that is voltage source shifting and the current source shifting. So let us consider the example for the voltage source shifting, how it will happen. So consider this network A. Okay, so there is a ideal source here. So there is an ideal source. You can see that. So this ideal source, why we call it as ideal source? Because it is not associated directly with any other resistor. So since it is a voltage source, so what we expect for a practical source to be? So the practical source will have, practical voltage source will have a resistor in series. But what you can see here, there is a node. Okay, so the terminals of this source E will be connected to two more resistors, but they are in the parallel combination. Okay, no resistor it is connected within this terminal A and B. So this will be considered as an ideal source. So suppose if we ask you to reduce this network, okay, with the source transformation technique, this source cannot be reduced to, or this network cannot be reduced to a smaller network. So by applying the E shift, that is voltage shift, we can reduce this network. So how we can apply? First, based on the polarity of the source. Okay. So first we have to identify for which node you will have a positive polarity and which node you have a negative polarity. So from the figure we can see that the positive polarity is towards B and the negative polarity is towards A. So this has to be maintained after reduction or the shifting also. Okay. So positive polarity for this resistor, it is connected to the B and negative polarity to the R. You can see that negative polarity is connected to R4 and positive polarity is connected to the node. So same thing we have maintained. Again, you can also, because the same voltage at this point we will find the same voltage. So this voltage, because this R4 and R5 are in parallel combination, so this will also have the same voltage at the node. Okay, so the node voltage will be remained same after shifting also. That we have to take care by looking at the polarity, and we can shift the source into two branches. One is R4 branch, another is R5 branch. But you have to make sure that the polarity should be maintained properly. So this is the E shift or the voltage shift. Similarly, current. Okay, so current shift. So in the current shift for the given network here, you can see that the current is flowing from the node A and it is coming towards the node C. So this current source, it is an ideal source because there is no resistor connected in parallel with this current source. So this will be considered as an ideal source. So this source can also be shifted like in this one. So here you can see the current can take so many paths. So for example, this path from A to C, A to E and A to D, E to D and D to C. That is A to E, E to D and D to C. So the source starting point is A and ending point is C. So that is maintained. Okay. So it is going from the A to E, then again from E to D, from D to C. So starting and ending point are retained as it is. Okay. Similarly, you can also try with the other path, that is from A to B, then B to C. So starting point of the current is A and ending point of the current is C. So that is maintained as that of the original link. Okay. So that is from the A to C. So this is how we do the voltage shift and the current shift, or in other words E shift and I shift. Okay. So we will take up some numericals based on this concept. So this is the numerical. Using the source transformation and shifting, find the voltage across 2 ohms resistor. So this we have to find out what is the voltage across 2 ohms resistor using the source transformation as well as shifting. Okay. So we will take up that one. So here you can see at the starting only. So you have one ideal source, current source and ideal voltage source. Ideal current source and ideal voltage source. Okay. So one by one we will take up. So let us consider the 2 ohms current source itself. Okay, the starting point is A and it is ending at the C. Okay, so we'll start from A, then to C. The value of the current will remain the same. So after applying the source shifting, you can apply the source transformation. So for this D and B, for the CD, okay, so you have next step in this is so it can be reduced after the applying the source transformation. Okay, so from current source to voltage source we have transformed. So let me erase the whole thing. Okay, so the current source is transformed from A to D, D to C. Okay, so then again voltage source can also be shifted from 3 volts at the connected at the B node to the 4 ohms and as well as for the 3 ohms. Okay, so another E shift can also be applied in the next step. Okay, so the reduced network after the I shift we have, but while shifting we have to be careful with the polarity. Okay, so in the next step again these two are in series, so we can combine. 3 ohms and 1 ohms are in series, we can combine. Again the 3 volts and 2 volts, okay, that sources are also we can combine. So look at the polarities, both are in the opposite polarity. So whichever the source will have the highest value, that the polarity will be retained. This is at the C. This also for source transformed into voltage source. So the circuit reduced as follows. Okay, so further we will reduce. Before that again we will combine these two by applying the source transformation from the C and B terminal. Okay, I'm going to erase once again. Okay, from this step we'll move on to the next one. So here again after reducing this into a source transformation, by applying the source transformation you have 2 amps as it is, 2 ohms, because we need to find what is the voltage across the 2 ohms. Okay, that is retained as it is. Then 4 ohms, 1/4 amps, 3/4 amps. So this circuit again it is transformed into this by applying the source transformation. Okay, voltage to current source transformation. So when you look at this one, you can also reduce this one into a single source. Okay, retaining the 2 ohms as it is. Okay, the equivalent R value you can find it as 4 ohms and 4 ohms, 1 ohms. Okay. So, 2 ohms, this one is 2 ohms. Again you have current sources, total current source. So the total current source here, we have to summarize this. So you have 2 plus 1/4 plus 3/4, which is equal to 3 amps. So this will become 3 amps. We know the current here, we have the resistors here. So we can find out what is the voltage across this. Let us call this as I1 and this as I2. Okay, voltage across this. So voltage across this we can be found out by main current I1 will be equal to 3 divided by 2 plus 2 into 2. So this will be CDR. Okay, based on this we can find out what is the I value. So once we find out the I value, we will find the V value as well. Okay, so let me erase this part. So V2 ohms equal to 3, that is main current, divided by sum of all the resistor So V2 ohms, okay, will be equal to 3 volts. Okay, this is the answer for this problem. So next we will move on to the next one. So all the diagrams, whatever I have written, it is shown here. So from the current transformations, current shifting, we have from A to D, then D to C. Okay, then we have again from the source, applying source transformation, retaining the 2 ohms as it is. So after applying the source transformation as well as the voltage shift, okay, E shifting, we get this diagram, reduction diagram. Then we will move on to the final one. From this we will obtain what is V 2 ohms as 3 volts. Moving on to the next numerical. So we have to calculate what is the voltage across A and B using the source transformation and the source shifting. Okay, so here also you can see that the terminal C and D. Okay, so here from this we have node A, B, C and D. So from the D, the current is flowing from the D to C. So either we can take a route from D to A to C, or from D to B, B to C also we can take a route. Okay, so here we have taken the flow of current from D to B, B to C. Okay, so when we take that, again we after applying the source shifting, when you apply the source transformation, so we have current source. Okay, so current source is 5 amps and there is a resistance. This is a practical current source. Then we can find out what is the voltage source value, practical voltage source value, that is I into R, that is 6 into 5 as 30 volts. And the polarity also you can note down that the polarity is from B to C. That means the positive polarity of the voltage source should be towards the C. Okay, and negative towards the B. In the similar way, this current source, practical current source, are also transformed into a practical voltage source. 5 into 2, so 10 volts. The polarity, it is arrow mark is towards the B. So the positive polarity of the voltage source will be towards the B, and the negative polarity of the voltage source is towards the D. Okay, so then after transforming, again we will rearrange the network. Okay, so since this is in series, so 6 ohms and 9 ohms will become 15 ohms here, which is also connected in parallel with the 3 ohms. Okay, and again this is also in series, 2 ohms and 8 ohms will become 10 ohms. Okay, so after converting into a 10 ohms, again transforming this 30 volts and 10 volts voltage source into a current source, we will get source value, the current source value as 2 amps. Okay, by transforming 30 volts with the 15 ohms, okay, and as well as 10 volts with the 10 ohms. So we transform, so we will get for the 10 volts voltage source, we will get the current source as 1 amps, and 30 volts voltage source will get the current source as 2 amps. So after reduction, we will obtain the current source, okay, difference between these two current source as 1 amps, and we have the 3 resistors connected in parallel. Okay. So now after this we can find out what is the voltage across these two, okay, by again by finding R equivalent. So R equivalent will be equal to 1 divided by 3 inverse plus 15 inverse plus 10 inverse. Okay. So R equivalent into I will be equal to VAB will be equal to R equivalent into I. Okay. So this will be the answer for this circuit. Okay. So next we will take up another problems in the next lecture series. Thank you.